சார் நீங்க ஸ்டார்ட் பண்ணிடலாம்.
சார் ஸ்டார்ட் பண்ணிடலாம் சார். ஓகே.
எஸ் சார்.
Okay, good morning everyone. Very happy and a cool morning. So we heartily welcome once again for you, once again each and every one of you for this third day STTP program, AICTE sponsored STTP program. So we feel glad to have Dr. Maiyalagan sir in our midst for today's session. A special hearty welcome to you, sir.
Thank you.
Let me brief the profile of our speaker. Dr. Maiyalagan sir, Associate Professor, Electrochemistry, Department of Chemistry at SRM Institute of Science and Technology. His research interest includes materials electrochemistry, fuel cells, metal air batteries, supercapacitors, electrocatalysis. So he has obtained his bachelor's from the Department of Chemistry at Loyola College, and similarly master's from the Department of Chemistry at Loyola College. Sir has obtained doctoral degree from the Department of Chemistry from IIT Madras. To his credit, he has around 70 papers, publications in reputed journals. Let me brief the academic experience. So he started as a junior research fellow at IIT Madras, and then a senior research fellow at IIT Madras from the year 2003 to 2007. He worked as an assistant professor, VIT University from the year 2007 to 8, research associate at Newcastle University, UK from the year 2008 to 10, research associate, Hydrogen South Africa, Cape Town, South Africa in the year 2010-11, research associate, Nanyang Technological University, Singapore in the year 11 to 12, research associate, University of Texas, USA in the year 2012 to 14, and senior research associate, University of East Anglia, UK, year 2015 to 16. His achievements and awards are upcoming. So in the year 2005, he has obtained travel award from the Department of Science and Technology to attend fuel cell seminar conference in USA. So he received the same award in the year 2008. In 2006, he has received Science Direct Top 25 articles for the journal Electrochemistry Communications. And his achievements keeps coming up, and we wish you all the best, sir. And we are happy to have you. And over to you, sir, for today's presentation. Please, sir.
Thank you, Professor. I'm audible?
Yeah, yes, sir.
Okay. Thanks for the Sairam Institute for giving me the opportunity. Today, I'm going to talk about metal air batteries, future electrochemical energy storage, and sustainable development. So today, the world is mostly facing the main problem is energy. The energy demand is particularly in Asia. It depends on both the economic impact as well as political impact. So many countries limited on fossil fuels. So the economic impact, as you can look at it, in Sri Lanka, the petrol price is different, whereas in India, the petrol price is, in Sri Lanka, the petrol is very cheaper compared to India. And when you go to Nepal and other countries, it is cheaper. So the economic impact and political impact drives the energy more greater. So if you want to develop a nation, the more particularly we need to develop the energy. So if you are having energy with less price, then you can achieve a more brighter economy. So apart from the energy, the economic impact and political impact, the energy we are using in the fossil fuels causes air pollution. So that causes climate change, and it leads to global warming. Delhi, air, which is clean air, which is Delhi in Delhi. And also we installed a tower which absorbs carbon dioxide in Delhi. That's what they go for gasoline as a fuel to emit less carbon dioxide. So apart from the global warming and these are the main issues in energy. So we need a clean energy. Instead of using oil and gas, we can go for a clean energy. That's the focus of our work. This is a Lisu forest city in China. They built 1 million plants and 40,000 trees. It is you can see that in the terraces, they even they build the plants in the terraces. So you can see that in this it's a CO2 free city. They announced as a carbon dioxide free city, which absorbs 10,000 tons of carbon dioxide and produces 900 tons of oxygen, and it produces 900. It's a carbon free city. So we need a carbon free city, that is environmental. This is one of the effort taken from the China. So we need a clean energy. So my research team is working on clean energy generations. We are working on fuel cells, water electrolyzers. Fuel cells is like producing water from hydrogen and oxygen. It's called the fuel cells. So hydrogen in the anode oxidation, the hydrogen oxidation takes place. The cathode oxygen reduction takes place. So this is a fuel cell. Opposite to the fuel cell is called the water electrolyzer. Same phenomena, but you are breaking the water. You can use a seawater and break hydrogen into water into hydrogen into oxygen, and you can generate electricity. So this is called electrolyzer. You can see some bikes have been generated have been running from the seawater using this water electrolyzer. This is a phenomena, and this fuel cell and still they used in 1860s in Apollo space mission, and this is the thing. And we are also focusing on metal air batteries. So in all the cases, these three devices, you can see the three devices: fuel cells, water electrolyzer, metal air batteries. All these three devices, these all the electrochemical energy devices, which is producing clean energy. In all the devices, you can see the main role here is oxygen. So the phenomena chemistry, as we look at the chemistry phenomena, all are involving the oxygen reactions in all the three devices. Clean energy generation, all the three devices, you're using an oxygen phenomena. Oxygen reduction takes place, oxygen evolution takes place. So the phenomena is oxygen evolution. So we will discuss mainly here today. We'll discuss about metal air batteries, where also here we're using oxygen reduction as well as oxygen evolution takes place in the metal air batteries. So all these are three phenomena, three devices. So as I said, in fuel cells, oxygen reduction takes place at the cathode. In metal air batteries, both oxygen reduction reaction, OER, oxygen evolution reaction. So oxygen has been reduced and oxygen has been evolved. Both reactions taking place at the cathode, anode. And hydrogen evolution, the water splitting. This is water splitting is in a water electrolyzer. You can see the water hydrogen evolution and oxygen evolution takes place. So in all these places, catalyst plays a major role. In all the devices, the main cost is due to the catalyst. The catalyst they use as a platinum catalyst. So how to select the catalyst? You need to have high surface area catalyst, electrical conductivity, and contact between the catalyst and the current collectors, nanostructure morphology, geometrical and electronic properties of the catalyst, and all are dealing with oxygen electrochemistry. And why we go for metal air batteries? The main issue is driving speed. The lithium-ion batteries, which is using in our cell phones, we can use it in a car. The main problem is safety issues and also the driving range. You cannot go more than 500 kilometers or more than 200 kilometers driving range. The battery and also the cycle life, driving range, charging speed, and also the safety. Safety is the main concern. The picture which shows the fire accident taking place at the Boeing in the Boeing airplane, US airplane. This fire accident taking place. After this fire incident takes place, people have been started thinking about more about the safety of these lithium-ion batteries. So these lithium-ion batteries, the safety is the main problem. That you can see in your mobile phone also. MI phones, there's been getting fired during charging and discharging. The lithium catches fire in this. So this is the main concern of this lithium-ion batteries is safety and then driving range. So that's why we are going for alternate batteries other than lithium-ion batteries in the storage. This is a video. You can see that MG electrical vehicle have been firing taking place in near Delhi. So as I said, safety is the main problem in lithium-ion batteries. So they awarded Nobel Prize for inventing the lithium-ion batteries, which are not good enough. But still, we need a higher energy density, and we also look for safety as well as cost-wise. And whatever the lithium-ion batteries we are using, the lithium resources is not available in India. We need to develop. We need to depend on other countries like China, and China is having the better resources apart from China and few countries. So the lithium resources we don't have much here in India. We need to depend on other countries. If you take Bangkok or Thailand, they have zinc resources more. So they go for zinc batteries. So now the trend is going for sodium ion batteries because we have plenty of sodium, and sodium is very cheap, and the raw material is very cheap. That's why we go for alternate batteries. Apart from energy, safety wise, we need to go for cheap resources. So the lithium ion having the resources having a problem, and also the safety issues, driving speed. If you drive a vehicle, you can drive only 160 kilometers. After that, we need to scrap the battery. That's why in the Tamil Nadu government introduced a vehicle. So if you want to charge, it takes more than 5 hours. You cannot wait and charge. The charging session is issue. That's why they swap the batteries. They have two batteries. If one battery is dead, the alternate batteries they will swap it. So you can drive up to 160 kilometers. This is the main disadvantages, and also the safety issue. Now we see the MG vehicle, it has been the firing accident takes place. So the major issue is safety as well as driving range and as well as energy density. So we need to go for future batteries based on the zinc or sodium ion batteries. But if you want high energy density, you can see the metal batteries. These are the developed. The blue color is all the developed available. Lead acid is available. Existing technology, lithium also technology, and the future will be the metal batteries, which is zinc batteries and lithium batteries. You can see the driving range is about 160 kilometer for lithium ion, for zinc as well as more than 225 kilometers. It's above the double the range. And when you look at lithium batteries, it is around 600 kilometers. So the future batteries, people are working on lithium ion as well as lithium sulfur. If you want to avoid lithium, then we need to go for zinc or sodium ion batteries. If you don't have lithium resources, then we need to go for sodium ion batteries or zinc ion batteries. So the research is focused on lithium ion batteries and sodium ion batteries. So this is a energy density map showing that how the Sony developed from 1990 the Sony patented the lithium ion batteries. After that, they developed is a major player in the lithium ion battery development. And then you can see that the future will be the sodium ion battery and the lithium sulfur and lithium ion. Though there's a high energy density, people focus on sodium ion because of sodium ion is available in the region. So we look at the energy density. These are the sustainable developments. Metal battery and sodium ion batteries are many sustainable development. And this is the below picture shows how the metal batteries taking place development. The first zinc air battery started at 1878, and then they reported iron air batteries in 1978. And then these are the developments of the electrodes and the catalyst development during this 1878 to 2018. So come back to metal batteries. As I discussed, it has high energy density, and lithium air is the highest energy density among all the metal batteries, and even it's higher than the petrol. So zinc air, aluminum air, iron air, magnesium air. If you replace the electrode by zinc by aluminum, it's called aluminum air battery. If you replace aluminum by iron air batteries. If you replace magnesium air battery. In all the cases, the major reaction is the metal. If you replace the metal, and this cathode will be the same. The oxygen reduction, the evolution will be the same. And this is the metal. Metal, if you keep on changing the air battery changes. So this is the theoretical specific energy density of all metal air batteries, and if you put including oxygen and excluding oxygen, and this is the open circuit voltage in the right hand side. Aluminum air batteries has a open circuit voltage is very less open circuit voltage. So when you look at the open circuit voltage, you can look at the lithium air batteries as the highest open circuit voltage, 2.91 voltage, and the energy density, theoretical specific energy density, including oxygen, is 5,210 energy density. So the lithium air is the highest And now people have been developing aluminum air batteries and zinc air batteries. Zinc air battery is the existing one. So zinc air battery, lightweight, not necessary to carry oxygen, high energy density. You can use the atmosphere oxygen for inexpensive, and it is very environmental friendly and safety issues. And when you compare with zinc air battery with lithium-ion battery, as I said, the energy density is higher compared to lithium-ion battery, which is using in a cell phones. The energy density is higher. So the negative electrode is always the zinc, and positive electrode is oxygen from air. Theoretical energy density is 1370, and the cell potential is 1.664. So in all the cases, if you want to improve the performance of any metal air batteries, the main performance depends on the cathode. Apart from the cell voltage, it depends on the anode. The other main performance depends on the cathode. The air cathode, it's called the air cathode, where oxygen reduction takes place. Oxygen comes from the air, it gets reduced, and also similarly, oxygen evolution takes place. Here, zinc forms the hydroxide. They use alkaline medium as a. If it is aqueous batteries, they use alkaline medium as a aqueous medium, and it forms when you use aqueous medium. Zinc forms zinc hydroxide, and these are the reactions taking place in the zinc air battery. So, as I said, the three cathode, air cathode, we need oxygen comes from the air. It reduces oxygen, reduces as well as oxygen evolution takes place. You need a three-phase catalyst, three-phase boundaries where the reaction taking place at the zinc air battery. So this is a structure where any metal air batteries, you can see what zinc, how it reacts with alkaline medium and forms zinc hydroxide, and this one, so you have a separator, and these are the reactions taking place. The cathode, you have oxygen reduction as well as oxygen evolution takes place. So if you replace zinc by aluminum, it's called aluminum air battery. If you replace zinc by iron, it's called iron air batteries. And if you replace by lithium, it's called lithium air batteries. So it depends on the batteries, maybe aqueous, zinc, aluminum, and iron, and other few batteries will works on aqueous medium. Whereas lithium catches fire, it works on non-aqueous medium. So these are the batteries, metal air batteries, and so the major components in any metal air batteries is air electrodes. The performance, as I said, air electrode is a electrode that there, where, here, these have the major drawbacks in the performance. And we have separator, electrolyte. Electrolyte depends on aqueous and non-aqueous electrolytes, and metal electrodes. And the metal electrodes is zinc. All these metal electrodes should have 3D structure, electrolyte. These are the issues, and these are the material design strategies. So during charging and discharging, few issues are there. One is the oxygen reduction and oxygen evolution takes place, and the mass transport. These are the how metal air battery performance depends on the materials. So major performance depends on the air electrodes. So these are the performance depends on the air electrode. As I said, it's called the air cathode. There you have oxygen comes from the air, where it reduces, oxygen reduction takes place, and oxygen evolution takes place. Oxygen reduction taking place during the discharging your battery, and oxygen evolution, that is oxygen has been evolved from your reaction taking place during recharging the battery. So reduction takes place during discharging, and evolution takes place during recharging. And if you take hydrogen, it has a 2 electron, or just electron transfer is very less number of electron transfer, whereas in oxygen electrochemistry, when you take it, it is a 4 electron transfer. So number of electron transfer is 4 electron transfer, and the kinetics of this reaction is very sluggish. So the reaction is very slow because of 4 electron transfer. So slow reaction taking place at the air cathode, and also round trip efficiency. The charging discharging efficiency is low rate capability. So you want to develop any metal air batteries, you need to choose your system, and also you need to choose the air cathode, develop the air cathodes, improve the performance of the air cathodes. To number of electron transfer is 4, so the kinetics is low. You need to improve the performance of the air cathode. Both oxygen reaction during discharging, you need to improve the performance. Oxygen evolution during discharging, improve the performance. So in this case, you need a electrocatalyst. Catalyst you need to break up this oxygen. You need a efficient oxygen electrocatalyst to improve the performance of the cathode. The performance of the air cathode. You need a better catalyst to improve the performance of the cathode. So the air cathode is very sluggish. You need to improve the performance. So you need a efficient catalyst to improve the sluggish, slow reaction, you need to improve the fast kinetics. So minimum is the voltage losses. So you need a bifunctional catalyst. Why we are taking a bifunctional? So it has taken two phenomena taking place, both oxygen reduction and oxygen evolution. Both reactions, both oxygen reduction and oxygen evolution taking place at the single site. It's called the bifunctional. So it has two functions. One is oxygen reduction taking place, other one is oxygen evolution reaction taking place. So you need a catalyst for the cathode, both bifunctional catalyst, whether it improve the performance of the oxygen reduction reaction, it should improve the performance of the oxygen evolution reaction. So you see the metal air battery is very simple, but you need to improve the performance. You need to focus on air cathode as well as other issues. The main performance depends, as I said, I stress the point, depends on the air cathodes. So if you want to zinc air battery, all these cathodes will be the same. Only if you change the metals, if it is change the zinc to lithium, it's called lithium air battery. If you change to iron, it's called iron air battery. If you change aluminum, aluminum air battery. The metals is very cheaper. That's why this metal air batteries are cheaper compared to other batteries. Take zinc air batteries very cheap than lithium air batteries, and the performance is better. So you need a both configuration of lithium air batteries. So oxygen reduction, oxygen evolution takes place during charging and discharging. You get oxygen from the air. So you get this oxygen from the air comes from the oxygen, go to the catalyst. And the catalyst, these are the oxygen comes from the air, goes to the catalyst and reacts, and both oxygen reduction and oxygen evolution taking place at the catalyst. So oxygen reduction reaction during discharging and oxygen evolution reaction during charging taking place at the catalyst. So the catalyst normally they use as a platinum and iridium catalyst. I will talk about the catalyst later. So this catalyst we need to develop it, and these are the compartments. How for iron air batteries, these are the compartment. You have a oxygen flow field. The air comes from the atmosphere in the air flow field, and this is air electrodes, and you have a compartment, electrolyte compartment, and this is an electrode. If you use iron, you can iron electrode. If you use zinc, you can zinc electrode, and again air electrode. So this will the cell assembly will be there for any zinc air batteries. So I am talking about the catalyst. The catalyst is the main issue here to improve the performance of oxygen evolution reaction. So you look at the oxygen reduction reaction. Platinum is the best catalyst till now for oxygen reduction reaction, but the cost is very expensive, and the platinum resources available in the world is very cheap, very less. That's why the cost is more compared to gold. Platinum cost is always higher because of the resources is less. And when you look at this is the best catalyst for oxygen reduction reaction. For oxygen evolution reaction, iridium is the best catalyst. So iridium is the best catalyst, but iridium is still expensive compared to it's expensive less than platinum, but it's expensive. So this for oxygen reduction and oxygen evolution catalyst, if you put this catalyst in your devices, it increases the cost of the devices. So you need a cheaper materials and which is available, transition metal based catalyst which is cheaper, and carbon based materials which is cheaper. We need to go for alternate catalyst. So when you look at this diagram, over potential versus this material, you can look at the material